Alright, so part 3 of our implicit notes is what are we going to do application-wise with our implicit derivatives. Now, most of the time when you take this derivative implicitly and you solve for dy dx, it's typically a quotient of two variable expressions, which will have x and y in it. Now, this just goes back to we're always concerned about where there are horizontal tangents, which is going to help me with extrema. Derivative is 0, but because it's a fraction, and I prefer to write it as 0 over non-zero to really emphasize what we're looking at there. So you look at the top of the fraction to determine when you have horizontal tangents. You set the numerator equal to 0. Okay. To figure out where you have vertical tangent lines, that's where your slope is undefined. Your slope is going to be undefined when you have a division by 0. However, notice it's not just division by 0, it's you're looking at the non-zero over 0 case. So you're going to set the denominator equal to 0. There is a caution about these, and I'm going to put this in red, which is no tangent line is going to exist if you get 0 over 0. So that's why we're going to look at these separately. If I'm looking for horizontal tangents, I'll set the numerator equal to 0 and figure out what my solutions are. And then I will plug them into the denominator and make sure that the denominator is not 0. And likewise, for the vertical tangents, I'll set the denominator equal to 0 and then make sure it doesn't make the numerator equal to 0. Now, I added something to these notes, is that you have to always remember that in order for this to even be a discussion, xy has to be a point on the original graph. And the reason why I put those in there is that typically when you are doing these problems, you actually end up with a system. And the system is, in this first case, equation 1 is set the numerator equal to 0. Equation 2 is the original equation, and these two things are going to make a system. Likewise, down here, you set the denominator equal to 0 and the original equation, and that's going to make a system for you. So that's kind of the little bit more challenging part of a lot of these, figuring out horizontal tangents and vertical tangents, is because you end up having to take into account that the function, the xy, had to be a point on the original graph, which means the original equation has to be true. And so it pretty much always ends up being a system. All right, so let's take a look at an example. Now, the first example is super easy. I do not need calculus to know this. If I have a circle centered at the origin with a radius of 2, I already know what this circle looks like. I know that I go 2 in all directions. I plot my points, I draw the circle, and I know what it looks like because we learned geometry. And if I were to ask you where there are horizontal tangent lines, you would say, well, there's a horizontal tangent line right there, and there's a horizontal tangent line there. So I already know the answer to the question, that the horizontal tangent lines are going to be at 0, 2, and 0, negative 2. Right? But notice that part B says, using calculus, verify that there are horizontal tangents. Notice that up here I did not use any calculus yet. And likewise, I also know that the vertical tangent lines are going to occur here and here. So the next part down here also says, using calculus, verify the vertical tangents are at 2, 0, and negative 2, 0. Right? So how do I use calculus? I am first going to find the derivative. I'm going to find the derivative implicitly, because I'm not going to, I could solve it for y, but I'm just not going to. It's way easier just to leave it like that. So our steps are, first, indicate that you are taking the derivative implicitly. By showing you're taking the derivative of both sides. Then you're going to notice everywhere that you have a y, you're going to need to use the chain rule and take the derivative of the inside. So my derivative of x squared would be 2x. Your derivative of y squared would be the derivative of the inside times 2y. And then the derivative of a constant is 0. So that gets you to there. Now it said find dy dx. So that means I have to follow this up with the step 2, which is I need to solve for dy dx. And again, it's pretty straightforward. dy dx times 2y equals negative 2x. Divide both sides by negative 2y. So we end up with our derivative dy dx is going to equal x over y. All right, I'm going to stop there because they didn't tell me to get it as a function of x only. They just said find dy dx. I found it. All right, so now using calculus, I want to verify that I have horizontal tangents at the point 0, 2 and 0, negative 2. So I initially look at this and I go, hey, you're going to write this on your paper. This is part of the problem. You go horizontal tangents occur when dy dx equals 0 over non-zero. Okay? You want to write that on your paper. Sometimes that's worth a point. So we write that on the paper. And now this has a really easy numerator. So I'm going to set the numerator equal to 0. This is not something you have to write. I'm just writing it for you. So I go x equals 0. And you go, yay, I set the numerator equal to 0. But then you have to remember that you're looking for the points. And so that's the first part of it, the numerator equal to 0. What else do we know? X squared plus y squared is equal to 4. That's your system. It's the simplest system that's out there. So what does that tell me the y values are? By solving the system, substitution. So I'm going to sub x equal to 0 in. I get y squared equals 4. Y equals plus or minus 2. So my points are 0, 2 and 0, negative 2. Super easy system on this one. All right, let's go down to our next question. We want to verify that we have vertical tangents at those 2 points. Again, we have to write our statement. What are we going to do? Vertical tangents when dy dx equals non-zero over 0. Again, this is worth probably a point somewhere, so write it down. Oh, and if I didn't say so, did I verify that the denominator of dy dx was non-zero? I did, because I found the y values. The denominator was y, and they were not equal to 0. Now, let's do this one. We get our first equation by setting our numerator equal to 0. No, sorry, denominator equal to 0. So y equals 0. And we have our equation as my system. Now to solve this, I plug 0 into the equation. I get x squared equals 4, x equals plus or minus 2. Clearly this makes the numerator non-zero, so my points are 2, 0, and negative 2, 0. Right. Now, the next thing that you could do is we could do something like, at what value of x is the slope 3/4? So they're asking me to set dy dx equal to 3/4 or x over y equal to 3/4. And the first mistake that you guys make is you tell me x is 3 and y is 4. But remember, I told you that this is always a system. X could be 9 and y could be 12. And this is still true, right? So you have an equation and you have 2 variables. You need to bring back your equation, and that is the system that you need to solve. And so typically what I would do is maybe let's do a substitution. It doesn't really matter. It says at what values of x. So I want to keep x in the problem. So that means y would equal 4/3 x from the first equation. And now I'm going to substitute that into the second equation. so that I can find x. X squared plus 4/3 x squared equals 4. This is going to give me 16/9. So I'm going to go ahead and make this 9/9. So 16 plus 9 is 25/9 x squared equals 4. I'm just solving for x, doing the algebra. X squared equals 4 times 9, which is 36 over 25. I multiplied both sides by 9 over 25. And then I square root, so x equals plus or minus the square root of 36/25 or 6/5. Right? Now if I go back to my picture to kind of see what this is, our slope is change in y, rise 3 over 4. And that happens at 6/5. So 6/5 is a little bit more here. Now notice it did not ask me for the points, and you will notice on this, here are your 2 points on the curve that correspond to 6/5 and negative 6/5. But the only ones that have a positive slope are going to be, let's do pink. Positive slope is here and here. So if they would have asked me for the point, I would have looked for the negative 6/5 and a positive y when I solved it. And then over here I would have done 6/5 and the negative y value from the solution if they'd asked me for the point. Alright, so that's example 7, kind of showing you how that's going to work in terms of an application. Now, just to recap, 1, you always state the statement which tells you what are you doing. This is when vertical tangents occur. This is when horizontal tangents occur. So you want to make sure you state that when you're looking at it. All right, then we start to get into functions that they don't have to be things like circles that we know. Here's example 8. I used Wolfram Alpha to sketch it, so that's our nice little elliptical kind of on a slant. Here's the equation of that nice elliptical right there, kind of complicated. And I want to determine the x values of any horizontal tangent lines to that graph. So visually, because I've graphed it, I know that it's probably going to be somewhere approximately here and somewhere approximately here. So I can eyeball it a little bit, but I do want to be able to find them exactly using calculus. So what we're going to do, you're going to first make your statement. All right. Horizontal tangents occur when dy dx equals 0 over non-zero. I add that extra over non-zero because I know I'm going to get a fraction on this. So I'm going to need to take the derivative, step 1, indicate that you are taking the derivative, 2x squared plus xy plus 4y squared, derivative with respect to x of 3. Implicit's not hard, but it's a lot of writing. Now I take the derivative. Remember that everywhere that there's a y, you're going to have to use chain rule. You might want to make a note to yourself that there's going to be a product rule right there. All right, so now we take our derivative. The derivative of 2x squared is 4x. Okay, the derivative of this middle term is going to be product rule. So I'm going to have the derivative of the first times the second plus the first times derivative of the second plus, now on this I need to do chain rule, so I take the derivative of the inside times the derivative of the outside, and the derivative of a constant is 0. So we get to there. I solve for dy dx so I can get it in the right form for that. I'm going to do a lot of this in as short of steps as possible. These dy dx's are on the same side, so that's kind of nice. I don't have to move them, they're already there. I'm going to go ahead and factor the dy dx out. X plus 8y. These items, I'm going to subtract them to the other side. So I'm going to subtract 4x and I'm going to subtract y. And then my last step, dy dx, is going to equal negative 4x minus y over x plus 8y. So that is my derivative. Now I go and I'm going to say, for this, we're going to now do the actual solving part. So usually I will say this is like part A of a free response, and then this is a follow-up question, part B. Find where the horizontal tangents occur. Horizontal tangents, I take the numerator, negative 4x minus y, I set it equal to 0. I bring the equation over, 2x squared plus xy plus 4y squared equals 3, and now I need to solve this system. They did ask me for the x values, so I'm going to solve this for y and substitute. Y equals negative 4x. Substitute it in, becomes 2x squared plus negative 4x squared, that's putting negative 4x there, plus, now be careful, I'm squaring negative 4x, which would be 16 times 4, so 4 times 16x squared is equal to 3. Collect your like terms. Alright, so we would have, I believe this is 58x squared equals 3, so x squared equals 3 over 58. So x equals plus or minus 3 square root of 3 over 58. Now notice it did not ask me to find the y value. Thank goodness. I'm not going to plug it back in. It only asked me for the x values, so I am done. And if you want to verify if you actually type square root of 3 over 58 in your calculator, it should end up to be something that matches approximately this area up here. The other thing kind of in looking at that, don't rationalize. You don't have to simplify. Just write that down, plus or minus. You've got your two values. All right, we're going to do the last problem. Determine the y values of any vertical tangent lines to the graph. So I already did the derivative up here, so I don't need to do it again. My system this time is take the denominator, set it equal to 0, bring your equation down. Okay, you might want to, I didn't say anywhere what I'm doing, so I would be like vertical tangents when dy dx equals non-zero over 0. Now, you should verify, and I did not do it, but I will mention it. You should verify that like this number, the square root of 3 over 58, if I plug it in there, does not equal 0. Because remember, you do have to make sure that it does not make the denominator 0. I will tell you when that happens on the AP, usually these numbers are much nicer, but you do want to make sure that you check, we'll just write it, check that the denominator does not equal 0, okay? But for the most, if you're running out of time on the AP, you can probably get most of your points without doing that. But I'm just going to mention you're supposed to. All right, I'm going to solve this system. This one said determine the y values of vertical tangent lines. So now looking at this, the y values, here's a vertical tangent line, so it's going to be somewhere here. Here's a vertical tangent line, so it's going to be somewhere there. I'm looking for the y values. All right, so in the interest of time, if I'm looking for the y values, in this one, solve it for x, because you want y in your equation. And then substitute it into your equation, so it would be 2 times negative 8y squared, which would be 64y squared, plus negative 8y squared plus the 4y squared equals 3. Combine your like terms, so this is what, 128, 120, and 116. 116y squared equals 3. Y squared equals 3 over 116. Y equals plus or minus the square root of 3 over 116. And again, I'm just going to make a note. You probably should check that the numerator does not equal 0 if you have time on the AP. Right? So that shows you those examples. And then, of course, I wouldn't be in calculus if I didn't ask you to find the equation of a tangent line. So our final example here is find the equation of the tangent line at the point 3, 1. So nicely, I already have the point. So I'm just going to underline it. I don't need to do that. So I just need the slope. I'm going to take the derivative implicitly. Show that you're taking the derivative implicitly by setting it up. Figure out where your y's are so that you are paying attention to the implicit part. Notice that you also have a product rule over here, and this has a chain rule involved in it. So taking the derivative is just starting to up the ante a little bit to make it a little bit more complicated for the derivative. So I start with the derivative of the inside, which is x squared plus y squared. So 2x plus dy dx times 2y. That's the derivative of the inside. And then 3g squared would have a derivative that is 6 times that g to the first. Over here we're going to do product rule. So I would do the derivative of the first, 100, times the second, plus the first, 100x, times the derivative of the second, dy dx. And I am not going to solve this for dy dx. I am going to choose to simply plug in 1, 3, 1 because I think it will be way easier with numbers. So I plug in 3, 1. That's going to give me, take each part individually, 6 plus dy dx times 2 times 6. And then I have my 3 squared, 9 plus 1 squared, 10 equals 100 times y, 100 times 1, so that's going to be 100 plus, my x is 3, so that would be 300 dy dx. And now I just need to get dy's dx's together because I have them on both sides. This is 60. I'm going to distribute. So 360 plus 120 dy dx equals 100 plus 300 dy dx. Collect like terms. Subtract 120 from that. Subtract 100 over here. So we end up with 260 equals 180 dy dx. So my final slope, dy dx, equals 260 over 180. I could simplify, but I'm not. If I wanted to, you're 26 over 18, and divide by 2, 13 over 9. So 13 ninths. But don't forget that you have to answer the question that they have asked you. And the answer to the question is the equation of the tangent line at 3, 1. And so y equals 13 ninths x minus 3 plus 1. So that's the equation of the tangent line. All right, one last example. We're tired about this one. I'm tired. But we are going to do this. Example 10. Notice they have asked me to find the second derivative. Find the second derivative. So to find the second derivative, I first have to find the first derivative. So I'm going to start the problem. The derivative with respect to x, 2x cubed minus 3y squared. The derivative with respect to x of 8. Take our derivative. Here's my implicit, going to be on that y right there. So it would be 6x squared minus dy dx, derivative of the inside, times 6y equals 0. Now, I will tell you that if you're doing the second derivative, you better solve for dy dx, because you can't take the second derivative until you have the first derivative. All right? So I'm just going to isolate dy dx. dy dx is going to equal 6x squared divided by 6y, or x squared over y. Now, once I have that, to get the second derivative, you are going to take the derivative of the derivative. So I'm going to take the derivative with respect to x of dy dx, and I'm going to take the derivative with respect to x of x squared over y. Again, why do I show this? Because I'm doing it implicitly, so I need to show that I'm taking the derivative. Notice that this is d squared y over dx squared, second derivative. Now I take the derivative of that, quotient rule. Low d high minus high d low all over low squared. Now, at this point, you might think that you can walk away. But here's where you have to be careful right there. Notice that I have a dy dx right there. Notice up here it said find dy, the second derivative, as a function of x and y. It did not say find it as a function of x, y, and dy dx. So you have one more step before you're done, which is I have to get rid of the dy dx, and luckily I'm just going to substitute. So 2xy minus x squared times x squared over y all over y squared. And now I have answered the question they have asked me. All right, that's the end of the notes for the implicit. Please check its learning for homework.